Good morning to all of you. So let us start our class. Okay. So I will just share the screen. So I think the screen is visible. So last class, we have started our plastic analysis. Okay. So we were discussing, of course, the design is fine, but how to do analysis, when the structures goes into this plastic range we have seen. Okay. So basically, there are three methods we have seen. The first method is, based on this incremental method we say, like, you increase the load, you do linear elastic analysis, you get the bending moment diagrams, and then you find out where bending moment is extremely high, say. Okay, so there is a chance of hinge getting formed. So and then you repeat the analysis. So once if it is a fixed beam, say, or if it is a propped cantilever, or this one. So we have seen where the hinge will get formed first. Like for example, this problem, say. So we know that the first hinge will be formed at this place. So now in the analysis, everything is fixed only. So you get the values, and then you find out where the hinge gets formed, and then and then this entire portal frame mechanism changes. Like this will be fixed here, and now this will be hinged actually. Now once again you do this linear elastic analysis, say, and then you find out the residual movements, and then find out where the next hinge will get formed actually. Okay, so like at 3 the hinge will get formed. So now you do the same problems, assuming these two as hinges, and this is fixed subjected to this load. Calculate once again the bending moments, and then you find out where once again the plastic hinge gets formed. So the next hinge gets formed here, and then the next hinge will get formed here. So like that, you do incremental method we say. So this method you can use, and you can find out this collapse load, for any portal frame or for any beam itself. Okay. Of course, this methodology is perfectly fine, but it is very tedious because if 4 hinges, you have to repeat the analysis 4 times, and but it is a computer programming and others. You can do very easily. So apart from this methods, we are also having some two simple manual methods. One is a static method, and then the kinematic method, which I showed you in the last class. All these two methods, they basically depend on these three criteria. One is the equilibrium, mechanism, and then yield. Okay. So now static method means it's equilibrium and then yield, and then the virtual work methods, say, like mechanism and yield, like that. So some of these conditions will be met also. So there is a theorems are there. Okay, somebody has already proved that if you use if it satisfies only the equilibrium and yield, say, then it becomes a lower bound. Then kinematic, because there may be several mechanisms may be there, so then this will be upper bound has been given. Then there is also unique theorem which says both of them converges if they satisfy all the three, like equilibrium, mechanism, and yield, say, then you may get the convergence also. So this also we discussed, and these are the assumptions I showed you in the last class, and mechanisms also we have seen. And then I think I already showed you this fixed how to do the analysis by static method as well as by the this kinematic method. So if you want to use static method, so first you have to draw the bending moment diagrams, but no need to worry about those values. Okay, so you can now you know where the hinges are going to get formed, say. So and you know how many hinges are also required for collapse, say. Okay, so what you can do at all those points, equate them to MP, and then you rework the equilibrium, or you equate it to this one, and then you can find out the collapse load. So like this I have already. So basically, so that's what we said. So incremental method. So this is one, this we have seen. So the incremental method, this is okay, step by step. Then other one is a static method. Okay, the other one is a kinematic method. So these three we have discussed actually in our previous classes. So incremental method, step by step, you do this one. Static method means you have to draw the bending moment diagram, and then wherever the bending moment is high, or where how many hinges are going to get formed. So yeah, you equate it them to the this MP, and then once again you solve, say, you will get to this one. Now in the kinematic method, say, so now we have to assume the the collapse mechanism, or how this beam is going to collapse. So here also I told you we will be using that rigid link, this one. So this mechanism has to, you have to assume a mechanism. Okay. So it is something like I already told you, eigenvalue, eigenvectors kind of a thing. You assume the mode shape, then you go back and find out what is the collapse load kind of thing itself. So this is essentially the virtual work method. Okay. So both are so these are the three main methods which are widely used. Okay. So these problems also we discussed in the last class. So if it is a fixed beam, say how to obtain from this method also, and then how to obtain from kinematic method also. And of course, both of them, if you have done satisfied all the conditions, both of them will give obviously the unique, the value itself. And this also we have seen like for a port, this propped cantilever, say. So static method means you just get the bending moment diagram from your linear elastic analysis. No need to worry about the values basically. Okay, and you know where hinges are getting going to get formed, and you know two hinges are required, so you equate them the moments, bending moments, the mp and mp itself, and then you do the equilibrium equations, and then you work it back, and then you find out how much load is required for the bending moments to be mp at this place, mp at this place itself. So this is how we try to do from the static method itself. And if it is a virtual work method, say we don't use any of these ones, so you just have to form a mechanism. Okay, so like two hinges are required, so you do like this, and you find out the work done, like internal work, external work, and then equate these two, and you will get the collapse load. So this example also, we have seen in the last class. Fixed, say three hinges are required. So this is a rigid link mechanism to the collapse mechanism. So you equate all those things, you will get back your this one. And now this also propped cantilever we have already seen, but there are two loads are there, say. So when you are having two loads, only number of hinges are maybe two hinges only are required. So you may be having several mechanisms, like the hinge may form, one hinge will form at the fixed support, one hinge may form at this load or this load. So you have to try all those possible cases itself, and then you can get the load. So this problem we have done using the static method. Okay, so static method means you draw the bending on diagram. So from the static method, so the bending moments at C and bending moments at this place are extremely high. So now you equate them to MP kind of a thing, you will get this one. Suppose if you take a wrong, let us say this was we told. So like let us say you assume hinges formed at A and B, say. So you will get alpha value, but when you check bending moment at C, it turns out to be more than MP, which violates your yield condition, because yield condition says at any point in your beam, say the bending moment cannot exceed the MP. So this condition gets violated. So now if you have plastic hinges at A and C, so that condition gets satisfied itself. So you find out all possible cases, and then you take the lowest this alpha value, and that is what your the collapse load. Now same things. If you have fixed beam already, we have done in our previous class. So static method means you draw the bending one diagram, and three hinges are required. Say so obviously and you equate all these things to MP itself, and then you do equilibrium once again, and then you get the analysis. But fixed beam, it is very simple. So it is a 2 MP will be equal to WL square by 8, and you can easily get these numbers itself. Okay, and if you want to do by virtual work also, we did already. So you just form a mechanism like this, and then you find out the work done, say. Okay, that is the internal work done by the load and the external work done by the load, and then you equate both of them, you will get these numbers itself. Okay, that's 16 MP by L square. And then we have already seen if it is a UDL, say, how to calculate the work done. Okay, so you equate if it is L by 2, say, you replace UDL by a concentrated load W into L by 2, and then you find out how much is the exact deflections. If you know this load, you multiply, so you will get the internal work done also. Okay, so this way you can do many problems. Now this is a very interesting problem. It is a fixed beam. Both the ends are fixed. Okay, so both the ends are fixed only. But the UDL, say, it is not like a symmetric in it is only existing up to some distance, actually 6 meters. So the span is total span of the beam is 8 meters. Okay, so the UDL is only up to 6 meters itself. Now we know from our the previous analysis, so determinancy is a 2, so 3 hinges are required, which we already know. And we can also say that one hinge may get formed here at these two supports. So where is the third hinge, say? That we are not of course you can do static method and you can do also, but where is the third hinge, say? So that third hinge location, the previous things was symmetric, so usually we can identify. Of course, here also if you draw the bending on diagram, you can identify. But if you want to do by kinematic method, say, that is not required actually. So what we do is we assume that a hinge gets formed at some distance x from this support actual. Okay, so here the hinge gets formed, so we can easily solve for this also. So let us say the hinge gets formed at a distance of x from this support actual. Okay, so now you divide this load into two pieces. So this piece you are having, you say 10 times alpha, so this is one this one. So this is other the load is on this portion also. So so now if you want to find out the work done by the load, say, So now, as already I told you, a simply supported thing, you can replace it with a concentrated load and you can find out the deflection. So the same concept if you use, so 10 alpha x, so this is at a distance of x by 2 from here. And this load, say, you replace it by a concentrated load. So 10 alpha into 6 minus x actually. So this portion is totally 6 meter is the where radial is acting. So x is here. So this portion is 6 minus x itself. Okay. So this is that. So you replace them by a concentrated load. Now you have to find out how much is the deflection here, so that you can calculate the work done basically. Okay. So you get this one. So now you can do some simple algebra like x. This is x say. So x times so this load. So x times beta should be same as the remaining portion multiplied by theta. That is 8 minus x into theta. So this gives you a link between theta and beta itself. Now if you find out the internal work done, say, so as already we know, and then to find out internal work, so three hinges are there. At all the hinges, the bending moment is MP. Here also it is MP, and here also it is MP itself. Okay, because this is what we said, and then it cannot exceed MP. So now the internal work will be MP into beta, then MP into theta, then MP into beta plus theta actually. Okay, so three things will be there. So MP into beta plus we have MP into theta. So this is at the supports. Then at this place, say, where hinge is getting formed, so MP into theta plus beta itself. So if we sum up everything, it turns out to be MP into 2 beta plus 2 theta itself. Now, if you want to find out the external work done by the load, say, so that means, so 10 alpha x is the load that is a concentrated, you have equated it to a concentrated load. Now you have to find out this deflection actual, okay? So this deflection is, x by 2 is at a distance here. So x by 2 into beta itself. So 10 alpha x, so x by 2 into beta. So this is the work done by this load. Now similar fashion, so you have to find out deflection here actually. Okay. So this also you can easily write in terms of theta, and then you can easily find out. So this turns out to be 10 alpha into 6 minus x, and 6 minus x by 2 plus 2 times into theta. So this is external work done by this portion of the UDL, the other portion of the UDL which is located other side of the hinge. So now you equate internal work to external works. Yeah, yes. So you equate internal work versus external work, and then finally, so you will get MP is equal to 5 alpha x by 415 minus 2x. But now we don't know still the x value itself. So what we try to do here is, we just maximize the bending moment to occur at d say. So that is, dou MP by dou x is equal to, you differentiate this one with respect to x, and if you solve a say, so you will get this equation, and finally you will get the x value as 3.75 times the 3.75 meters itself. So once you know the x value, so that means your hinge is going to get formed at a distance of 3.75 from your fixed support, that is from the NDA. So once you know this x, say, you go back, you substitute, you get MP, and you solve for alpha, say. So you will get to 2.84 is our value itself. So what it tries to tell us is, the working load, say, if it is a 10, say, so the beam can still take load up to 28.4, the kilonewtons per meter. So this way you can easily find out, if you don't know the location of the hinges, but if you know it approximately where it is going to find. So using the kinematic method, say, you do internal work, external work, the same thing continues, but you can use, you can assume the hinge at a distance of some x, and then you find out the total moments, and you maximize it, you calculate x, and then you go back, and then you find out your collapse load and plastic movement and other things also. So this way you can easily do this type of problems itself. Now let us say one very interesting problem, that is for continuous beams itself. Okay. So now generally in continuous beams, what happens is, we have to know the words like partial collapse, complete collapse, and then over complete collapse actually. Okay, so there are three types of collapse mechanisms are there. So generally, we know already that if the redundancy say is R, so this is our redundancy. So we know these many hinges are required actually. Okay, for complete collapse of the beam, like for fixed beams, we have seen redundancy is a two plus one, so three hinges are required. If it is a propped cantilever, say, so redundancy is one, one plus one is two, so two hinges are required for complete collapse of your the beam itself. So when it comes to the continuous beams or portal frames or whatever we will see here, suppose if the number of hinges say, are smaller than these r plus one, so this is something like partial collapse actually. Okay, so complete collapse means if both of them are same, maybe complete collapse, and if the hinges are sometimes you may require more number of hinges also more than this r plus one. So that is what they call as over complete collapse also. Anyway, we will not go into these details. You will study these things in great detail in your advanced structure analysis course. Okay. So right now for continuous beams, what we try to do is, so this entire beam collapse is different, but if one span collapses, like AB, just AB collapses, that's what we call as a partial collapse. So this span may be there BC, but AB collapses, or AB is fine, BC collapses. We call this as a partial collapse itself. So this that itself is the collapse for our the continuous beam itself. So this in this problem set, it's a continuous beam, two spans are there. So now we have to find out the collapse load. So what we try to do is we will do partial collapse only, like collapse of AB we calculate, collapse of BC we calculate, and then we try to find out which is has the lowest load, which will collapse first. So that is itself is our collapse load for our continuous beam. The only thing here is when you try to do this continuous beams, so you have to analyze span AB separate, span BC separate. Now, so this bending moment at A anyway is zero, bending moment at C is zero, the bending moment at B is not zero. It acts like a fixed kind of thing. So when you try to analyze ABC, it is like a propped cantilever. So B is fixed, A is hinged, and then you find out your propped cantilever, this concept itself. Okay, so one hinge gets formed, one hinge gets formed. We already know two hinges are required for propped cantilever to collapse. So you equate, say, so MP, and wherever hinge is getting formed, moment is MP. So MP into theta, MP into theta plus theta, that is three times theta, and the work done by the load, say. So the load is three times PW, span is, the L2L is this L into theta. So this is a collapse load for span AB only. So in a similar fashion, so you do for BC also. So B anyway is a fixed kind of thing. One hinge gets formed, one hinge gets formed. So MP is our this one. So MP into 3 theta, and this is span is 2L here at 2 4L, 2L is this one. So this becomes 2L times theta. You solve it, so you will get 1.5 times MP by L itself. Now for BC to collapse, load is 1.5 MP to L. For the AB is MP by L itself. So the lowest is, or the most critical span is, that the AB span only. So MP by L is a collapse load or the partial collapse, you can say, for this continuous beam. So this way you have to do for continuous beam. So if there are more spans are there, say, you have to isolate. Like here you are having three spans, say. So you take this portion, you take this portion, you take this portion, do it separately. But one thing you have to clearly say is, suppose if you are taking this span, say, this bending moment may be zero here, but bending moment may not be zero. And so this you have to analyze as a propped cantilever, whereas this portion, so both the things are like a fixed kind of a thing itself. So you have to analyze using that concept. And here, say, you have to use, once again, the propped, the cantilever kind of, sorry, propped, that this one you have to cantilever itself, and you find out loads for this portion, this portion, this portion, and the lowest is your collapse load for this beam itself. Okay, so this way you have to calculate for continuous beams. So when it comes to portal frames, say, portal frames is very interesting, and of course the incremental method, whatever I told you, that may be easy, like you can do step by step. But if you want to do by kinematic methods for simple frames, you can easily calculate by this method itself. Okay. So like for example, so you can have a beam mechanism. So generally in portal frames, if there is a vertical load, say, beam mechanism can happen actually. It may be on a beam or it may be on the column. Suppose if it is like this, so you can have a beam mechanism here at determined to collapse itself. And sway mechanism happens for horizontal loads. Okay, so then there are horizontal loads on your portal frame, say. So the hinges may get formed, at all the four, and then it will lead to sway mechanism also. Then you can have a combined mechanism like beam plus sway. So this also is a possibility actually. Okay, so generally for portal frames, what we try to do is When vertical loads means beam mechanism will be there, horizontal means sway mechanism will be there. If both horizontal and vertical are there, say, you may have to check for a combined mechanism also. And depending on the redundancy, you know how many hinges are required and you can easily calculate. So let us see this problem. Okay, so this is a portal frame. You have vertical load and you are having horizontal load. Vertical load means, so this portion you can have a beam mechanism here, but whereas this portion, because of the horizontal loads, you can also have sway mechanism also. So both the mechanisms are possible. And here also you have to, one more important thing is, for beam mechanism to happen, say, generally three hinges itself are sufficient, but for this portal frame, redundancy, because both the things are fixed, redundancy is a three. So three plus one means four hinges are required. Okay, but for beam mechanism, say, three hinges itself are sufficient. It is like a partial collapse, you can say. Now for sway mechanism, all four are required. That is a complete collapse itself. So now let us calculate for both the mechanisms. So for a beam mechanism, say, so it has to three hinges, it has to go like this. So MP, 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 wherever hinges are there, say, you equate it to MP. Now you find out the work done. So MP into theta, then MP into 2 times theta, MP into theta. So you will get 4 MP times the theta, and then you find out work done by the load. So this deflection say. So since the span is, I think I already mentioned, right, 3L. So this turns out to be 3L into theta here. So you equate this to this one. So P is 2 by 3 into MP by L itself. Now for sway mechanism, so four hinges are required. Okay, it's like a complete collapse kind of thing. One hinge here, one hinge here, all the four supports. Now you calculate. Okay, so MP into theta, MP into theta, MP into theta, MP into theta, and the work done by the load is, so this deflection say is 4L is the length of the column. So this becomes 4L times theta. So you equate both of them. So you will get MP by L itself. So this is the load, collapse load for sway mechanism. So if you compare this and beam and sway, say, so this is lower than the MP by L itself. Now we have to check for combined mechanism also. That is a beam plus sway. As already I told you, for complete collapse, is a four hinges only are sufficient. So when you are having a combined mechanism, so one hinge will be there at both the supports hinges will be there, and here also hinge will be there, and here you will have a hinge at the the load itself. So here there will be no hinge actually. Okay, so this will be still 90 degrees only to maintain that this one. We will calculate also, draw the bending one diagram also. So four hinges itself are sufficient. Sometimes there may be some problems, say. We will not go into detail as far as this course is concerned, but if in advanced structure analysis, you will see, like, sometimes the five hinges may also will be required. So that type of things happens, like when the beam is stronger than the column, like MP for beam is 100, MP for column is some 20 or 30, or maybe they are different say. Then you can have even a over complete collapses also are possible. Anyway, that is beyond the scope of this course only. Okay, so four hinges are required. So two hinges, this hinge, and here is your hinge itself. So now you calculate. So MP into theta, MP into theta, MP into 2 times theta, then MP into theta itself. So 6 MP times theta, and work done. Say. So this is a 4L times theta, and this is 3L times theta. So you calculate. So this is our collapse load. So now we have seen for beam mechanism, it is 2 by 3 MP by L. For sway mechanism, say, it is MP by L, and this is a 3 by 5 times MP by 5L. So now among these three, say, the lowest is this one. So that means, this portal frame, say, is going to collapse in combined mechanism only. So like that, we can easily find out, you see, all this collapse load for all the mechanisms and find out the critical load. Yeah. And now once you have found out these loads, say, you can go back and you can check actually. Okay, like we have used only the mechanism condition, and based on that we have calculated. So now we know the collapse load. Okay, so 2 PW. So now you draw the bending moment diagram, you use equilibrium, and the bending moment at all these places, say, like it is bending moments are already known to MP. Then here also it is MP, and here also it is MP. So now you draw the bending moment and shear force diagram, say. So you take this portion, that is D. So this portion, so these are the reactions, and this one, so EX, EY, and then you have a movement, but that is because it is a collapse load, it is equal to MP. So here also hinge has formed, so MP dx dy. Then if you take this portion, say C also, it is MP, CX, CY. You can calculate all those things from equilibrium equations, MP plus MP minus EX, say. So this combination you take, okay, for EX horizontal, this one. So you can calculate EX, the support things and all those things from our these expressions. And these are the support things like EX, EAY, all those things you find out. Now we will find out what is the bending moment at B. It is still, it has not plastified itself. So you use your ordinary, whatever linear elastic analysis, you find out. So the bending moment at B, say, turns out to be 3 MP by 5. So which means, they expect the bending moment at B is below MP itself. It is not more than MP itself. So which means, so this is perfectly fine. Just one second. Hello? Hello? Tell me. Yeah, is a phone call. Okay. Yeah. Yeah. So now you can go back and then you can find out all the what is the bending moment at B also, at the point of collapse itself. So this turns out to be MP by 3, MP by 5. You can draw the bending moment diagrams also. So at the collapse, say, so all these places MP, 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 MP will be there. But at this place, you will have still 3 MP by 5 itself. So you can go back and you can check, the bending moment diagrams, and you can so it is very easy, So once you have got the collapse load, say, so you are the hinges MP, MP, MP. It is like, going back. You know the bending moment, but you are going back and trying to find out the loads and then try to find out the bending moments at other places itself. Okay. And now this is also a very simple problem, same as the previous case only, but both are horizontal loads only. Okay. So now how many mechanisms? So now both are horizontal. So now you can see there is a chance of beam mechanism also. Okay. So beam mechanism can happen in the column, not in the beam actually. So because of 3P say, this load is acting at the center, so there is a chance of beam mechanism. Now apart from this one, because both of them are horizontal say, so there is a chance of the sway mechanism also can happen, and you can have a combined mechanism also. So let us try to find out this problem itself. So this is what we are calling as a beam mechanism. So beam means partial collapse. So 3 hinges are required here. Then you can have a sway mechanism, which means 4 hinges, like the previous case. So this also can happen. You can have combined mechanism, that is beam plus sway. But only thing is here, the load is not acting on the beam. Load is acting at the center point of your this one. Suppose if 3P was not there, say, then you will be having only one mechanism, that is a sway mechanism. Because of 3P, the load is acting at the center of the column. Say. You can have a beam. That means the column is also like a beam kind of a thing. Then you can have a combination also. So this is a combined mechanism, like one hinge here, one hinge here. So this still it is a no hinge here, 4 hinges only. Okay. So this you have to find out for all the three cases itself. So it is very straightforward. So this is simply MP into theta. So MP into 2 times theta. So MP into theta. So 3P times you have to calculate. So this you will get as 2 by 3 into MP by L. And sway mechanism say MP into theta, MP into theta, MP, MP, MP is there at all the 4 places. And you have to find out a 3P also contribution will come, and 2P also contribution will come. Okay. So this turns out to be 2 by 7 times MP by L itself. Now you can have a combined mechanism also. So this is slightly straightforward only. So everywhere it is MP, MP only. So you have to just calculate, the load given the relation between theta and beta itself. So this is a relation actually. 2L times theta is same as 4L times beta, and theta is a 2 times beta, and you calculate. So work done by the load this one. So you will have 310 MP by L itself. So now if you calculate, say, among all the three mechanisms, the lowest one you can find out. So that is a critical mechanism. That is how this portal frame is going to get collapsed itself. So this way, you can solve, many problems, just using kinematic methods. You assume a mechanism, and then, you go work back, and then, you find out your collapse load, and you can redraw the bending one diagram, and you can verify also. Okay. So similarly, so you can solve several problems itself. So this is static method and the kinematic methods is say, okay, whatever we discussed. static and kinematic methods. So for simple problems, you can use for simple problems. And suppose if you're having a frames like this, say complicated multi, frames. So if you're having multi-story or these type of frames, so then you can have so many mechanisms, so this partial collapse of this one, then you can have a joint mechanism and so many mechanisms you may have to consider. So for these type of things, the incremental method which I showed you in the starting, that may be easy for computer programming and other things. You can use these methods also, but you may have to do so many mechanisms and you have to be careful. So among all the mechanisms, say, which is the lowest, you have to take care into your calculations. Okay. So I think with this, this topic, almost we have come to the closure of this topic. You will learn about this plastic analysis in great detail in your advanced structure analysis course, where they will be teaching you how to analyze these type of frames, for plastic analysis, and how to find out the collapse load for these type of frames itself. So fine. So with this, I close our class for today. So all the best, and then have a nice day to all of you. And if there are any questions, you can ask me.